Welcome back to COMP526, Efficient Algorithms. We look at a new unit, again around strings, but this time we'll try to squeeze space, try to compress it and store text with as few bits as possible. It's a different perspective from what we've had before, but we'll see there are some connections. It's again a mixture of things you may have seen. If you had some undergraduate classes, then the first third or so you may have seen, and then we cover some more recent things again that find their use in up-to-date tools on, for example, the PCR tests, finding little reads of RNA in your genome, things like that. They make use of these techniques these days. But before we get to that, a few basics first. Till the end of this, I want you to understand a bit deeper what we've covered already a bit, that characters have to be encoded as numbers in a computer. I want you to take away that there's limits, at least if what we'll talk about will be lossless compression. So there's some hard limits to what we can do. And then there's a list of things, little tricks and techniques. Looks like a long list, but some of them are really simple and easy. I want you to roughly know what these are. And the goal is as well, give you a set of standard tools that you can apply and tweak to a certain scenario, because that's often what you will have to do. You have some type of data in an application that has certain properties, and none of the methods directly captures that, but with some slight tweaks or a combination of things, you can make use of that. All right, let's start with a bit of context. Some of this I said already. We're still talking about strings. The last couple of units were mostly about how to compute, and we focused a lot on finding patterns in a long text in various ways, right? What we assumed in that, in all of these units, was that our strings are like arrays of characters. So I can, in constant time, jump to character number 10,175. That's one memory access because I know the position, so I have some. In low-level speak, there's a pointer to the beginning of the string, and then I add an offset, and that gives me the character at that position. That was implicit in all the algorithms that we used. Some of the algorithms don't need that. They can also read it sequentially. In this and the next unit, we'll briefly look at how to transmit strings and save space there. But a more recent trend actually is to bring the two things together. I'm not sure if I will have time to talk about that much. But as a little spoiler, if you want, a lot of the things have been brought together with slightly more sophistication maybe than we can cover. You can work on a text that's compressed, and it's a little bit like if you had a zip file and you could still treat it as if it was uncompressed. If you play around with a huge zip archive on your computer, you may notice it looks like you can jump and pick out any file. But what your computer has to do is decode from the beginning until it finds the file you're looking for and then copy that out. And if you have a really, really big archive or a slow hard disk or something, it takes quite a while. And there are much better ways to do that, but they haven't made their way, at least, into standard operating systems. Because we're such a lovely mixed group, I thought before talking about many of these methods, let's see which ones you know. Let's say by know, how do we define know? Having heard about it in some lecture, that's probably a narrow definition. Yeah, there's a few that are definitely coming up later again. Cramp is always good. I deliberately made the question fairly vague. Like, compression methods could mean many things. Some of the things you send are file formats, which have some form of compression built in. Some others, I'll just ignore it. Some others are algorithms that by themselves are not directly implemented, but form the basis of other things. What you can't see again, what you cannot see is the numbers. So 7 people sent lossless, that's the biggest blob. So overall, it's still, sometimes these look like, okay, everyone has seen, you know, JPEG, but it's really just 2 people. The graphic makes it looks a bit more widely known or widespread. Okay. I'll keep it open. You can keep entertaining yourself if the rest is already known to you. The boring bits first, to make notation concise and to give it the mathematical flavor that I like so much. Let's introduce a little bit of terminology first. We'll always talk about a source text. That's the thing we start with. And that will be called S. And so we have a certain alphabet. It's a string. It comes from an alphabet, so its letters come from a certain alphabet. And that's called the source alphabet. We write it as sigma S because there's also sigma C, which is for the coded text. Now you will say, hold on, if we're compressing, I usually just have some file on my computer. It's binary at the end. So why do we keep that general? We'll see that sometimes the best compression methods result from chaining different things together. And so there's intermediate stages where it's just more convenient not to go to binary straight away. So we'll keep it general. Question?
Yeah, for each compression algorithm must actually make some strings longer, because if you have a string of n characters and you want to compress it to 2n-1, they are at most, you can only compress half of the n characters to 2n-1. Like,
yeah, sorry, so if
you can't compress all, you have to, some them actually become longer. If you're doing lossless compression, at least some strings of a particular length must become longer after compression than before.
Yeah, so I want to cut you short there because it's part of the tutorials. Yeah, the comment is you cannot always compress in the sense of getting shorter. I think I have some comment on the slide later as well. But it depends a bit on the assumptions. You need lossless compression. In the general case, just some source text goes into some coded text, just to have names for the things. And then, well, we say encoding goes from S to C, and decoding goes from C back to S. Now, sometimes you can get precisely back the source text that you put in. Then we talk about lossless compression. That's what we will focus on. But there's also lossy compression where you lose some information. So the decoding is only approximately what you put in. You don't get the source text back bit by bit, but something close to it. Now you will ask what close means, and I'll pass that back to you and say depends. It's usually useful for data that has some other meaning beyond just the bits. So multimedia in some form is the usual. And then JPEG is the one for pictures, and an MPEG, or, well, it's a bit dated, but newer video codecs do the same for video. They try to exploit the usual type of pictures and videos that people have. So JPEG compression works well for photos of real things. If you put in a picture that has random bits, red and black and white or what other color, it wouldn't compress that well. And same for video. If every frame is completely different, it wouldn't work well. It exploits the fact that if you film some scene, usually from one frame to the next, from one picture to the other, there's only a small change or some movement that you can track. But still, these formats are lossy. They throw away detail in a way that is usually not perceivable or not perceived as a big difference by humans. The thing is, there's at least as much psychology involved in these parts as there is computer science. So I'll leave those out, and we'll focus on the parts that are a bit more amenable to these fundamental rules.
Question.
Yeah.
Yeah, you mentioned that they throw away detail. From an information theoretic perspective, did they like throw away significant? Is the like approximate preservation? So a JPEG usually keeps most of the features that are important to humans.
Yep.
I'm wondering if the information preserved is also like objective in that, okay, these are the features that are actually like important. If you try to like look at the bits, like say like a not necessary human independent view of, okay, this information that's preserved is actually what is important, or is it like arbitrary? Is it like, I mean, like, can you like formulate the how much information is lost versus conserved,
right,
purely abstract terms without like referring to humans?
I would summarize the question as, can you somehow take the human out of this lossy compression approximation? I don't think so. I mean, maybe you can take out the human if you have a precise definition of what similar means. And for some data, that maybe that's doable. I mean, I could make up an example. Say you compress English language text, and you say, I don't know, I don't care about how words are properly spelled. As long as it has the same phonetic pronunciation, I accept it. That's somewhat well defined, I guess. It doesn't need a human necessarily. Let's pretend there's a single way to pronounce all English words, right? First abstraction. Then you could try to define something like that. It wouldn't be super lossy. It wouldn't be super interesting either. I think that that part is closer to lossless compression of something else, namely the actual pronunciation in that case. So some sequence of sounds. I mean, if you could just decode that and throw away the text, I think there's an underlying lossless task hidden in there. And the lossiness really often comes from the fact that we don't know exactly what we want to keep. That's my my impression of the two. If you look very closely, some of these definitions are a bit vague. Okay, shall we move on from that part? So for us, the goal will be lossless. We want to do this for computers, so they should get bit by bit back what you put in. Then the question is, you can cook up many things. You can decide, today I'm doing it this way or that way. How can we judge whether an encoding is good? And that again depends a bit. Just to make that clear, you could have different things like an encoding should be secure, so that someone who just sees the coded text cannot easily get the source text back. That's one way of encoding. You wouldn't normally call compression something like that. That's called encryption usually, but it's in the same framework. What we'll talk in Unit 8 a bit about is what if you want to tolerate some noise in the coded text and still recover what you put in. What we'll focus on here mostly is the size. So we only care about how many bits we need. That's what usually people mean when they say compression. And to operationalize that a bit and give us a term we can work with, we define the compression ratio, which is effectively the size of the coded text divided by the source text. But we have to be a bit careful because we're working with different alphabets. And so the proper way to define it is to take as many characters in the coded text times log of the alphabet size, because you roughly need that many bits to write down one character. If these are nice powers of 2, you can actually just write it down like that. So the typical case, as noted here, if the coded text is in bits, then this simplifies log of 2 is 1. And for the source text, we usually stick with the alphabet. Now the compression ratio can be less than 1, or greater than 1, or equal to 1. In general, everything can happen, and only when we have less than 1, we have actually achieved something in terms of saving space.
Yeah, sorry. Regarding integrity, can't you just like take a hash of the source and then decode it and then compare? Like, let's say you want to transmit a message, and you can just like send the hash of what the message should be, and then the recipient can compare the message to the hash and see if it differs.
Sure.
Yeah, I'm not sure. Like, I see the point to have like integrity features in the encoding itself. Right.
Okay, so that's on this point. The question was, can't you just send some hash of the message alongside with the message as a way to detect modifications? I mean, that's definitely a solution that people use, right? Now, it depends a bit what you mean by hash. There's a hash, but hash is kind of not well defined. Usually you mean some cryptographic hash function, like MD5, even though that's broken, don't use it anymore. SHA-1, probably still safe if you long enough, and so on. I don't want to get into these too much. So if you never heard about these, they won't show up on the exam. These are functions that are designed to be one way. If you put a text in, you get the value out, but there's no easy way to get a given value. How do I have to change the text to get that value? And that's important, right? Otherwise, if I just do a simple, say, a parity or some simple function of the text, count the number of characters, say, I can change the text so that the hash stays the same, and you wouldn't notice that change. So I think what you suggest, including this cryptographic hash as part of the coded text, that is the integrity check, right? That's what this means. Question?
Yeah, so the difference between compression algorithm and cryptology is the focus. This algorithm focus on size, and cryptology focus on security.
Yeah, definitely. Yeah. So we'll focus on the number of bits that we need, or the compression ratio, and so on. And often these things, several things are important, but you can apply them one after the other. You first zip your files, and then you send them via encrypted email to your friend, or I don't know if you still use PGP encryption, if anybody still does, or some other way of encrypting. You can often separate things out and do one after the other. You don't normally have to worry about them at the same time. And again, turning this into a cryptography course, I'm tempted, but let's not. Is another big interesting topic with its own techniques that we will basically not touch on. Other questions? Then let's have a look whether you're, this looks like unrelated for now. Let me leave it without much comment for now. There we go. Oh, is Post's correspondence problem. Yeah, look it up. It's a lovely little computational problem. I mean, while people are voting, it's basically you have pairs of strings. There's a top string and the bottom string. And the question is, you have a set of such pairs. And the question is there some way to take any sequence of these pairs so that you put one pair, next pair, and so on, so that the top string, if you read across all the pairs, and the bottom string are the same? Is it possible or not? You're given fixed set of pairs of strings, and that's all I'm asking. It turns out no computer on this planet can do it. Not even any conceivable computer in any of the computational models that we've come up with is able to do that. Because in a way, these pairs of strings can simulate all computation that we know of.
That reminds me. Yeah, that's a question.
Yeah.
Again, on computability. Most of the uncomputable problems I'm familiar with, like Rice paradox, the Hawking problem, they are due to self-reference. Are there uncomputable problems that don't feature self-reference?
I think the PCP is the closest I could point out. Yeah. You're right. Many of these problems have this kind of diagonalization. I think PCP is an example that's not quite as obvious of that kind. We had 50 people vote earlier. I don't know. Shall we wait till 40? But it seems a lot of people haven't heard about it. So in short, uncomputable problems or undecidable problems are just questions that have a definitive answer, like this one that I just described. If I give you pairs of strings, either it's possible to somehow form a sequence of these pairs so that the top part and the bottom part reads the same, or it's not possible because you somehow always produce more text in the top one and you can never catch up with the bottom string or something like that. But it turns out you can prove mathematically rigorously that no computer can solve these. No computer, given this as an input, can come up with the answer either definitively yes or no. And there's several such. The halting problem is the most famous one. No computer program exists that can take an arbitrary other computer program and inputs and tell you whether it ever terminates or not. It's fundamentally impossible. And the reason for that is that you can basically feed a description of that program to itself that drives it into a contradiction. You can create a program that calls this hypothetical program and does the opposite of what its prediction is. And that way you can prove that it's not possible to have such a program in general. Again, this is lovely stuff. Did I post this Veritasium video about the Gödel's incompleteness and so on Campus Wire? Because that covers these as well. It's in the later part of that video. It's lovely theory and so on. We don't really need that here, but I thought, depending on how many people are familiar with this, I might point out a few connections there. It comes into the topic of compression in the following way. If you're given some data, for example, the image on the right, you can ask, is this compressible? Again, in the sense of lossless. I don't want to throw away information. I'm not interested in JPEG or PNG or something like that here. Can you compress it? And well, if you look at the picture, it looks complicated. Some areas are maybe, this is all white, so maybe that's all right. But then the rest looks pretty complicated. And you know these fractals, you zoom in, right, and it becomes...
Most fractals are defined by like mathematical equations. So you could probably...
Exactly.
Probably just like get the equation that creates that fractal instead of like storing
Yep.
the
That's exactly the point. In one way, the image is really complicated because even just predicting what the color at a certain area is quite tough. On the other hand, there's a fixed formula that generates this image. in fact, this one was generated by a fairly small program, and you can make that generate as much resolution as you want. So what should the answer be? Is the image compressible or not?
Yeah.
In a way, yes, because it has a small program that generates it. And so the most versatile notion of compressibility is give me a program that generates the data for me, and the size of that program is my code. It's a fairly intricate code. That's much different from zip. Maybe a self-extracting zip archive comes the closest. But that's really just a little piece of program that tells you how to exactly handle that specific file format. It's by far not as sophisticated as this one would require. So the most general notion goes by the name of Kolmogorov complexity. And it just says ultimate compressibility is the length of the smallest program that produces the data in terms of prints or something like that. Now that sounds great, right? Let's just use that. I mean, why not? And the problem is that finding this complexity is uncomputable in the same sense as these other problems I mentioned before. It's completely hopeless in that sense. Question?
So, yeah, I heard that for Commodore complex, like if you change the choice of universal machine, there's like it at most has a constant. So
Yeah. So
to be able to like approximate it, so like get good estimates of program does. But if you have like a short program for a, let's say you have like a short program to print an image in a particular language, in a particular universal language, then you have like this forms like an upper bound on what the Commodore complexity of that is.
yeah, what I should have said is I glossed over what that means. What's the length of a program? I mean, you're probably thinking of some Python program, and it's just the length of the source code, right? But you could maybe write a shorter Python program that does the same. And in a way, this made it sound like it doesn't depend on the choice of Python over Java over whatever else. And in a way, there's a general theorem that tells you in an asymptotic way it doesn't depend on the language. But there's a lot hidden here. In a way, any proper language would do as a definition here. Doesn't matter too much. But it's also equally useless in the sense that any proper programming language would also make the problem uncomputable. And that's why we haven't dealt with the topic yet. That's why there's many of these methods following. What people have done instead of going for the ultimate compression is find tricks that exploit some redundancy in the data to get smaller representations. And so the focus is on things that always work or can always be applied, but might not always reduce the size as much as possible. But that's the best we have. So we can ask what are features that can make data compressible in a sense that we can deal with, not in this, there's a hidden fractal if you look at it in 5 dimensions and through the right angle. Things that we can easily find. And there's 2 things we'll discuss. One is, remember, we're talking about text. If some characters are much more frequent than others, we should try to take advantage of that. For example, English text has lots of E's and not so many Z's. So you should try to give E a shorter representation. That's a simple thing you can do. And the other, yep.
Question. Yeah, sorry. This is going to like drag us back. So let's say I have a string of length K, for example, a string of length N. I know that there exists a compression of that string that is length N, which is just the string itself.
Yep.
So something you could do, which is not incomplete, you could search over all programs that are less than N and see if you find, you could like start from searching over all programs of length 1, then all programs of length to see if you find a program that produces that string, and that is not uncomputable, but like it's a finite set. Although it's like not efficient.
Well, the problem with that is, okay, so I think we have to stop the digressions as fun as they are, but this last one, so the question was, suppose I have a string of length n, can't I just enumerate all the programs up to that length?
Yeah.
And then I should find if there's a shorter one.
First, you start from the shortest. The first program you
Sure. I mean,
is the shortest program.
the problem with that is, how do you decide whether a program that you're now looking at generates that string? In general, there's nothing better than running that program, and it might never terminate.
Oh, yeah.
And so that's how that fails. Yeah, I mean, I appreciate the attempts. It won't work eventually in the general case. That's proven already. But maybe it's helpful to think about these things a bit. So keep going. Just don't try to reach for the impossible. So that's something that I'll just announce here, and you will work on this in the tutorials a bit. There are certain, I call them no free lunch theorems for compression. Some things are just utterly impossible. It looks like you can always compress, but what I encourage you to do is take whatever data, zip it, take the zip file, zip it again. Have you ever done it? Like, zip is great, right? It should compress. So if you zip it again, it's even better. Anyone ever tried it?
But like not in this context, so like
you want to try it out and tell us what happens?
you actually just like create a zip bomb. Like you can take a string, a text.
That's a different problem, yeah. So zip bomb is a good thing to Google. That's the opposite direction. You can have a very small file that unzips to an absurdly big thing.
Yeah.
That's all right.
Like zero entropy, just like a string of all ones, and then just like.
I would call that a great example of compression, right? It means zip works. It can massively compress some boring files. What happens if you zip a zip file again is it gets a little bigger. Not much, but a little bit. And I guess internally it basically is there's some header information and then the rest of the file remains roughly unchanged.